Welcome to Lesson 3, Reflection 2 from the Light and Sound section. In this first part of the lesson, we're going to be doing part 1, which is reflection at curved surfaces. In the last section, you were looking at flat or plane mirrors. Now you're going to be looking at curved mirrors. And there are two types of curved mirrors we're going to look at. We're going to be looking at concave, very like the mirror in the diagram in front of you, and convex mirrors. Let's start by looking at concave mirrors. How do you make a concave mirror? Well, if I take a sphere or a football and I turn it into a mirror so that the outside of the football, that's the back of the mirror, the non-reflecting part, and the inside of the mirror, that's the reflecting part. So if you shone a torch in there, the light would go all over the place. There's the center of my sphere. So how do I make my concave mirror? I get that sphere and I cut off a section from the mirror. So let's say I cut off that section there, and then I bring it over here. So there you can see, there's the mirror, and here's my center from that mirror. That's my concave mirror now. So let me look at some definitions. Well, C is called the center of the mirror, or more fancy than that, it's called the center of curvature. If I take the entire length of the mirror from up here, we'll call that point A. Down to the bottom, we'll call that B. That entire length of the mirror, the distance AB, that's called the aperture of the mirror. You hear that quite a lot when we talk about optical instruments. And then if I go halfway down from A to B to that point there is called the pole of the mirror. If I draw a line from the pole out to the center, this line here, this is a very important line. This line is called the principal axis. One more line, I suppose, one more thing we could talk about is the radius of curvature. The radius would be the distance from C to the pole or to any part on that arc. That there represents the radius. I suppose more fancily we say the radius of curvature. So R stands for the radius or the radius of curvature of my mirror. So now let's explore that mirror in a little bit more detail. I want to shine light onto it and see what happens to the light. So once again, here I've got a concave mirror. I'm going to draw in, once again, my principal axis, which will go from the pole out through the center. There's my principal axis. I'm going to shine a ray of light onto that mirror. The ray of light I'm going to choose is a ray of light that is parallel to the principal axis. So take a line here, a ray of light, parallel to the principal axis. That is my incident ray. Where does that ray end up going? Well, I'm going to use my law of reflection. My law of reflection says that the angle of incidence is equal to the angle of reflection. But how do I find out where the angle of incidence is? It was easy enough to do when I had a flat mirror. Now I've got a curved mirror. How do I draw the normal to the surface of that mirror? Well, you probably know from maths that if I draw a line from the center out to the circle, those lines will be at right angles to the surface of the mirror. So here's my ruler. I'm going to draw this line here. That line I've just drawn is called the normal. It's perpendicular to the surface of the mirror. And therefore your angle of incidence will be this angle in here. It's always the angle to the normal. And we know that the angle of incidence is equal to the angle of reflection. If I draw an angle here, that is the same as my ray of light will bounce down like that. There's my reflected ray. So this here is my angle of reflection, and I is equal to R in that case. Now that ray of light passes through a very special point called F. F stands for the focus. And actually, most rays of light parallel to the principal axis and fairly close to it will pass through the focus. So if I draw, let's say, another ray of light that's parallel to the principal axis, this ray of light here, that will pass down through the focus as well. So all rays of light parallel to the principal axis and fairly close to it will pass down through the focus. Okay, so you know a ray of light going parallel to the principal axis, you know where it's going to end up. It's going to end up getting reflected through the focus. So, ray of light parallel to the principal axis, you know it goes down through the focus. You see, we want to be able to draw images in concave mirrors. So I need to know what's going to happen to a number of rays. And this is my very first ray. So I actually know now that all rays parallel to the principal axis will go down through the focus. So I'll call that ray A. These are called construction rays. You're going to use them to actually find your images later on. What about another construction ray? Well, just think of the opposite of that. If instead of setting the ray of light in parallel to the principal axis, let's say I sent it in through the focus. Light is reversible. So if I send a ray of light through the focus, what's going to happen to it? It's going to be reflected out parallel to the principal axis. That'll be my second construction ray. Take any ray of light, like this one, that's actually passing through the focus. It goes through the focus like that. What happens to it? It goes out parallel to the principal axis. And now I have two construction rays. We call that one ray B. We'll just go for one more that you occasionally need. So my third ray is this. I want a ray of light that goes straight at the mirror. Like if you sent a ray of light straight at a plane mirror, it'll bounce back along its own path. The angle of incidence will be 0 and the angle of reflection will be 0. How do I send a ray of light straight at a curved mirror? Well, how do I draw normal to a curved mirror? It's a line through the center. So if I send in a ray of light through the center, do you know what happens? It bounces straight back along its own path. Because the normal will be there. What's the angle of incidence going to be? 0. What's the angle of reflection going to be? 0. So it comes back along its own path. So we will call that ray C. So using those three rays, we should be able to draw any image we wish inside a concave mirror. Let's go back to our notes and have a look at that. So in our notes, you have your construction rays. So there's ray A, parallel to the principal axis, is reflected through the focus. Ray B, a ray of light through the focus, is reflected out parallel to the principal axis. Ray C, a ray of light through the center of curvature, that's straight at the mirror, will bounce back along its own path. Right, now what you want to do is you want to draw images that are formed in concave mirrors. Now you get all kinds of different images depending on where the object is placed in the mirror. In your notes, I want you to draw these along with me. They ask these quite a lot in the physics exam. They ask you to draw an image of, let's say, a magnified image in a concave mirror, or a magnified inverted image or real image. We'll get to all that later. So I want to bring you through all the different ways you can draw an image in a concave mirror. And of course, when we do this, we're going to be using our construction rays. Our 3 construction rays will be used. Let's start with the first one. Let's start by putting an object outside C. So putting an object outside C, I'm going to represent my object by an arrow. That there represents my object. So I want to form an image of that object. Well, I'm just going to form the image of the tip of the arrow. I want to find out where the tip of the arrow finishes up, and then all the other points will follow behind that. So, my first construction ray is, I always say, this is my first construction ray. A ray of light from the tip of the arrow, parallel to the principal axis. Where does it go? It gets reflected through the focus. Now, in order to form an image, I need a second ray. I'll take my second ray, which is a ray of light through the focus, will end up going parallel to the principal axis. So once again, from the tip of the arrow, take a ray of light going through the focus. Where does that ray of light end up going? That ray of light will end up going out parallel to the principal axis. Find out where those 2 rays meet. They actually meet here. The tip of the arrow finishes there. It's actually upside down. If I did all the other points, which I'm not going to do, they would finish back here, going back to the principal axis. There's my image, I. What are the properties of that image? The properties of the image are called the nature of the image. The nature of I. Well, the first thing is, this will be a real image. And how do I know it's a real image? Because the rays of light actually meet. We did a virtual image before where the rays of light only appear to meet. We had to work them backwards. Here they actually meet. So the first thing I can say about the nature of my image is it's a real image. Real images can be formed on screens. What's the next thing I can say about it? I can look at the size of it. I want to compare the size of it to its original. There's the original there. It looks smaller. How do we say smaller when we talk about photography? We say it's diminished. So it's a diminished image. And the last thing I'll say about it, you can see that it's upside down. It's inverted, not laterally inverted, actually upside down. So the final part of its nature is inverted. Actually, you will find that all real images will be inverted. So if it's real, then it's also inverted. That's your first one done. Now what's going to happen is I'm going to push that object in closer and closer and closer and see how the image changes. The next thing, number 2, I'm now going to place my object at C. Now, this one is a little bit tricky to draw because I'm going to tell you right now what the answer is. I'm going to tell you where the image is. The image is also at C. and it's going to be the same size. So I'll give you a little trick. In order to get it absolutely right in the exam, actually draw in your image first. Same size, upside down. There's my image eye. I'm doing a little bit of cheating in order to get it absolutely right. Once again, let's take our two construction rays, the first two. A ray of light parallel to the principal axis. Where does it go? It goes down through the focus. And you can kind of ensure that it goes through the tip of the arrow as well. So there's my first ray of light. What's my second ray of light? From the tip of the arrow through the focus. Where does it end up going? It ends up going out parallel to the principal axis. We put a line out parallel and make sure it goes to the tip of the arrow. So there's my image formed. And what can I say about the nature of the image? Well, once again, I can say it's real because the rays of light actually meet. What else can I say about it? Well, here it's neither diminished nor bigger, so we say it's the same size. And the third part of it is, well, it's also upside down like the first one. So it's inverted. Now we keep on going. I'm now going to push the object in a bit closer again. I'm now going to put it between C and F. So here's my third diagram. So I'm now going to place my object here between C and F. I'll take the same two construction rays, ray A and ray B. So ray of light, parallel to the principal axis from the tip of the arrow. Where does it go? Well, it goes out through the focus, goes down through the focus. And what's my second construction ray? A ray of light from the tip of the arrow through the focus. Where does it go? It gets reflected out parallel to the principal axis. And where do these two rays of light meet? Well, these two rays of light meet in this position. The tip of the arrow finishes there, and all the other points will finish back here. You can see where it finishes. It finishes outside C. What's the nature of it? Well, it's real again. You can see the size of that image compared to the original object. It's bigger. And what do I call bigger? I call bigger magnified. And the last part, of course, if it's real, it's also inverted. So what have we got so far? So far, when I place the object outside C, I get this diminished image between C and F. When I place the object at C, I get an image in the same position also at C. And then, when I push the object in even closer between C and F, well, the image ends up outside C. So now let's move on. So I'm moving the object in closer and closer. So now I'm going to move it to F. Well, I'll take my first ray of light as usual. So from the tip of the arrow, a ray of light parallel to the principal axis. Where does it go? It gets reflected down through F. What about my second ray of light? From the tip of the arrow through the focus. Well, if I take it from the tip of the arrow through the focus, it's going to miss the mirror. So now I'm going to take my third ray of light. And that's a ray of light straight at the mirror. Straight at the mirror is through C. So if I take a ray of light, like that, going through the tip of the arrow from C, so I send it through C, and what happens to it? It bounces back along its own path. What can I say about those two rays of light? Those two rays of light are actually parallel. They'll never come together. Also, if you try to work them backwards, because they're parallel, they'll never meet. So you don't get an image there at all. Basically, if you say something like, I can't even write down its properties. I'll just say the image is at infinity. And when you look at it, well, you'll see a bit of a blur because no proper image is formed. So it'll be blurry looking. And finally, let's move our object so it's inside F. So I'll take two construction rays. I'll always take the first one from the tip of the arrow, a ray of light parallel to the principal axis. What happens to it? It gets reflected down through the focus. What's my second ray of light? From the tip of the arrow through the focus. Well, actually, that won't work. From the tip of the arrow through the focus, we'll just miss the mirror. So we take our third one. Our third one is straight at the mirror. So straight at the mirror is a line through C. So put your ruler, C, tip of the arrow. So if I send a ray of light from C through C, hits the mirror and it comes back along its own path. So have a look at those two rays of light there. These two rays of light will never meet to the left. They are diverging. However, like we said in the plane mirror, if I get somebody's eye here, their mind's eye, they're going to work those rays backwards. So in their mind's eye, these two rays of light will be worked backwards, and they will appear to meet somewhere back here. So the tip of the arrow appears to finish up here. Let me just put the principal axis, let me extend it to the right-hand side. And all the other points in that arrow will go down to the principal axis, as so. So there's my image. And what can I say about that image? Well, what's its nature? The first thing, is it real or is it virtual? Well, it's obviously virtual because the rays of light only appear to meet in your mind's eye. It's a virtual image. What about the size of it compared to the original? Well, compared to the original, it's much bigger. It's magnified. And the last thing, it's not inverted, sure it's not, it's the right way up. So it's an upright image. Actually, you will find that all virtual images end up being the right way around. They are upright. So they're the 5 different image formation diagrams that you need for concave mirrors. You got to know these inside out. There's a worksheet on your website for actually practicing these. How will they ask these in the exam? They might say to you something like, draw a ray diagram of a concave mirror to show how a virtual image is formed. And that's what you would do there. They might ask this question. They might say to you, draw a ray diagram to show how a magnified real image is formed in a concave mirror. And now you're talking about number 3. They're not going to say draw 1, 2, 3, 4, 5. They're going to frame it the way I just said. So you have to know which of the diagrams I need to use. Let's have a look at image formation in convex mirrors. So we've already looked at the concave mirrors. Now the convex mirrors are the other way around. How do I make a convex mirror? Well, once again, I'm going to take a sphere or a football, but this time the back of the mirror is going to be inside and the reflecting part of the mirror is going to be outside. And what am I going to do? Well, from that sphere, I'm going to cut off part of it. Let's say I cut off that part there, and then I take that part and I bring it over here. Well, there's the center of the sphere, also called the center of curvature. And we bring it over here, and there's the center of that arc that I cut off. Once again, we'll go through the definitions. The entire length of the mirror, from A down to B, that's called the aperture of the mirror. And then if I go halfway down there, I get to a point called the pole P of the mirror. And then if I draw a line from the center out through the pole, we call that line, as we did with concave mirrors, we call that line the principal axis. Now, what do you see? You see this time the center of the mirror is actually behind the mirror. Let's have a look at a ray of light. The ray of light I'm going to take is a ray of light that's parallel to the principal axis. So I'm going to send a ray of light in. And of course, this is the front of the mirror now, so the light has to go this way. If light went back here, you'd see absolutely nothing because that's the back of the mirror. So I'm going to take a ray of light that is parallel to the principal axis. What happens to that ray of light? Well, as you might expect, given the shape of the mirror, that ray of light is going to bounce up towards the sky. But it doesn't bounce up in any old way. If you do your calculations by working out the angle of incidence and the angle of reflection, which I'm not going to do here, I do for the concave mirror, well, it bounces up as if it came from a point, and that point is called the focus. So there's the ray of light bouncing up. But as I said, it doesn't bounce up in any old way. It bounces up as if it came from a point. You're going to work that line backwards. That point down there, that will represent the focus F. So once again, the focus is behind the mirror. We actually call that a virtual focus. More about that later, because it's behind the mirror. And basically, all rays of light that are parallel to the principal axis, where will they end up? Well, they'll end up being reflected. They can't go through the focus because the focus is behind the mirror, but they'll be reflected as if they came from the focus. So I'll put my ruler down like that. I'll have the focus along it, and here's my ray of light getting reflected. And there's the broken line showing where it came from. So all rays of light parallel to the principal axis will get reflected through the focus. Now, once again, let's talk about construction rays. What's a construction ray? It's a ray whose fate I know where it's going to end up. And as a result of that, I can form images in convex mirrors. So I'm going to look at 3 construction rays, A, B, and C. Well, what's the first one? Well, the first one is what we've already said. A ray of light parallel to the principal axis. What will happen to it? It will be reflected as if it came from the focus. That's ray A, your first ray. What about my second ray? Well, light is reversible. So basically, if I go the other way, if I send in a ray of light as if it's heading for the focus, it can't actually get there, of course, then it's going to be reflected out parallel to the principal axis. So here's my second ray. So I'm going to take a ray of light, any ray of light, heading for the focus. But it won't get there, of course. That ray will hit the mirror and bounce out parallel to the principal axis. So that's my second ray. And then my third ray, we talked about this with concave mirrors as well. A ray of light straight at the mirror. And what does straight at a mirror mean? Straight at a circle? Well, it means perpendicular to the circle. So if I'm going to send in a ray of light that is perpendicular to that circle, then it is a line going towards the center. And what happens to that ray of light? That ray of light will bounce back along its own path. So there, they are my three construction rays. So these are in your notes. So they're all explained very well there in your notes. Ray A, Ray B, and Ray C. So now I want you to use your notes to actually show how an image is formed in a convex mirror. You can draw it here with me. In order to draw my image, I'm going to pick two of my three construction rays. I just need two. Find out where they meet, and that will locate the image for me. The one I'm going to use is ray A ray parallel to the principal axis, is reflected as if it came from the focus. We'll use that one. You could use B if you want, but I actually prefer to use the third one. A ray heading for the center of curvature C is reflected back along the same path. So I'm going to use A and C when I actually do it. So let's see how it's formed. Unlike concave mirrors, we did 5 different diagrams. So there was different positions for the object, and they gave rise to different image formations. You had virtual images, real images, magnified images, diminished images. The one thing about convex mirrors is you always get the same kind of image no matter where you put the object. So let me put the object somewhere in front of the mirror, the left of the mirror. There's my object O, which I represent by an arrow. I'm going to work out where the tip of the arrow finishes up. And if I know where the tip finishes up, I can work out where all the other points in the arrow finish up. So I'm going to take my first ray. And what is it? It's a ray of light parallel to the principal axis. And what will happen to that? That will be reflected as if it came from the focus. So I'll put my ruler like this. The ray of light gets reflected in that direction as if it came from the focus. There's the broken line back to the focus. That's my first ray. Now I'm going to take my second ray, ray C, a ray of light heading straight at the mirror. That means towards C will be reflected back along its own path. So here's the tip of the arrow. So put your ruler from the tip of the arrow towards C like that. So my ray of light will go towards the mirror and then bounce back. And here's my broken line back towards C. So there's my 2 construction rays. Now you can see those 2 rays there, they are never going to meet. They are diverging. But they may meet in someone's eye, in their mind's eye. So if I put someone's eye here, we will work them back from where they came. So we'll work that one back this way, and we'll work this one back this way. And you can see where they meet here. So the tip of the arrow actually finishes there. And if I did all the other points, which I'm not going to do, they would go along there. I put it in broken because it's only an image in your mind's eye. I can't form it on a screen because it's not a real image. Once again, we talk about the nature of the image. These are the properties of the image. And what's the first one? Well, the rays of light only appear to meet. You know what that's called? That's called a virtual image. Next, look at the size of the image. I'll call the image I, of course. Look at the size of the image compared to the original. There's the original there. You can see the image is much smaller. So much smaller means it's going to be diminished. All images in convex mirrors are diminished. finally, well, you can see that the image is the right way around. So I say it's upright. Actually, you'll find that all virtual images are upright and all real images are inverted. So they are the properties of a convex mirror. So there's only one diagram that you've got to do. Okay, so what I need you to be able to do, and this is important, I need you to be able to practice doing all your mirror diagrams. So there's going to be a worksheet on your website. Download that and practice drawing the one image you need in a convex mirror. And then further back, you've got the 5 different images that you get in a concave mirror. Know them really well. How will they ask the questions in the exam? They might say something like, draw a real magnified image in a concave mirror. They might say, draw a virtual image in a concave mirror. They might say, draw an image in a convex mirror. They don't have to specify what kind of image because there's only one kind of image that you have to draw. Finally, in this part of the lesson, let's look at some real-life applications of curved mirrors. So I want to look at some real-life application of concave mirrors and convex mirrors. Starting with concave mirrors. Some of their applications are car headlamps, floodlights, and projectors. Because what happens is they produce a nice parallel beam of light instead of the light going off in all directions. Now, how can concave mirrors achieve that? Well, there's a concave mirror and there's the focus. You know this already, don't you? You know that rays of light going parallel to the principal axis are reflected down through the focus. Well, what would happen if you did this? Let's say in a projector or a car headlamp or a floodlight where you want a nice narrow beam of light. Let's say you place your light source right there and shining light out in all directions. Well, let's take one such ray. So here's a ray of light leaving the focus. What's going to happen to that ray of light? You've guessed it. That ray of light is going to go out parallel to the principal axis. Because the opposite is also true, isn't it? A ray of light going parallel to the principal axis will go down through the focus. So the rays of light that are coming off that light source placed in the focus, they head towards the mirror and they go out parallel to the principal axis. So what you end up getting is a lovely parallel beam of light instead of the light going all over the place. So very good for floodlights, very good for projectors, very good for car headlamps. Let's look at the next application. That can be used in shaving or makeup mirrors. Think about this. Think back to your image formation in concave mirrors and think back to the last diagram that you did. The last diagram we did was we placed the object inside the focus. I'm not going to draw the rays of light again. We've already done them. What did you end up getting? You ended up getting a virtual image, an upright virtual image, and magnified. So as a result of that, that makes it very, very handy for makeup mirrors, where you obviously want to see an upright image of your face. You don't want the image to be upside down when you're putting on lipstick. Shaving mirror. But what has to happen is your face has to be inside the focus. So the focus has to be sufficiently long to allow that to happen. So basically, we can use a concave mirror as a makeup mirror because if you place your face inside the focus, you will see an upright image, a magnified image of your face. A dentist will also use it because you can imagine you put that into someone's mouth and you get a magnified image of somebody's tooth, and it's the right way around. And finally, let's talk about convex mirrors. Well, these convex mirrors, you'll see these convex mirrors in the corner of supermarkets to stop people robbing things, because you're going to get a full view of the supermarket. They're used as rear view mirrors in cars. The reason for that is they have a wide field of view. So let me explain why that is the case. So for example, there's my convex mirror. There's the back of the mirror. We've already talked about when rays of light come in, they're going to bounce up or bounce down. They're going to diverge. Well, why is this very good for use in a supermarket where you want to get a wide field of view and see the entire supermarket? Well, if you take rays of light coming from one end of the supermarket, they're going to bend in, bounce in towards a point like this. So point in there. And if I take rays of light from the other end of the supermarket, back here, they're going to bounce in. They're going to bounce in towards the eye of the observer. So whoever's standing there can actually see all the rays of light coming from one end of the supermarket down to the other end of the supermarket. So you can imagine big buses, side view mirrors on big buses. You get a wide field of view as well. That's their advantage. They do have a disadvantage though, because you know that the kind of image formed in a convex mirror is always diminished. So you've got to be aware of that. If I'm driving my car and my side mirror is a convex mirror, well, what I'm seeing behind me is a diminished image. And as a result of that, I might think that car is further away than it actually is. So you need to be aware of that. Okay, so that's the end of the class. Thank you very much.